Now we will see how to solve the secretary problem or the marriage problem or the special problem where we pick the best among the n pieces of paper. Okay? So, I am sure many of you would have thought about the best way to do this, and it is very common that people think of some way of exploring first and then exploiting. Now, we will use this word exploration and exploitation a couple more times during this course. The idea is that you will first explore and see how the numbers look like. Okay? You will keep rejecting them just because you want to get some samples. Let's say you are someone who has never hired a secretary in their lives, would think about, okay, now how do I go about this? I have no idea who would be a good person to have. So you will explore a little bit. You'll try to see how the lay of the land is. Okay? And then you learn from experience. Then you would exploit. By exploit sounds like a bad word. Basically what we mean by that is once you learn something, you'll say, okay, I'll come up with some rule and then I will adopt it. Okay? I will make sure that I try to get the best secretary possible. So that type of a strategy where you would reject a few people for a while, and then once you find a good a good person, you would hire them, is a strategy that a lot of people would come up with for this. But how long do we explore? Now that's a question that I don't know if you would have thought right off the bat. Now, so my question is, how long? I mean, you don't want to go on exploring. Out of the n, the first few you want to explore, and then for the remainder you want to exploit. So it turns out the optimal stopping rule, and this is among all the policies, this is the optimal policy when n is large. Okay? So what you would do is you would reject the first n over e. So n is the number of papers, e is the usual natural logarithms base. Okay? So e, if you remember, is 2.71828 approximately. And what you would do is you would start with, so you would reject the first n over e. Of course, n divided by e may not be a round number, so you would round it down and reject all of them. Starting with the next one, you will say, okay, we will look at this, see if this is better than everything we've seen so far. If that's the case, you would accept it. If it is not, you will reject that and go to the next one. Okay? And then see if that is better than everything you've seen that far. If it is, you'll pick that. Otherwise, you will reject it and you'll keep going this way. Okay? So essentially, you will see the one that is better than all the previous ones and accept it. So that is your stopping rule. You will stop when you found one that is the largest thus far. Okay? Now, this policy, like I said before, is not guaranteed to give you the optimal solution, because what if the largest one shows up in the first n over e? That's it. Then there is no way for you to select it. Okay? It could also happen that you the first n over e is is such that you didn't get too many of the large numbers, and then the very first one that was larger than those you picked, but there may be others that are coming in the future. So we don't know that, so it's not guaranteed that you would do well. But among all the policies that you could think of, this one is going to be the best. So let's do a little example. So let's say n is 25. Now 25 is not tremendously large. However, I mean for the purposes of the proof of the optimal policy, however, it is good enough actually for illustrations, and also when you put it on a screen, it's easy to see some of this. So what you would do is you would reject the first 9. So 9 is 25 divided by e. Okay, that's the number that's the nearest to that. And we'll reject the first 9 of them. Then starting the 10th, you will look and see which is the best we've seen thus far and go ahead and pick it. So think of the following. So pretend like these numbers are revealed one by one. First the 12 is revealed, so you open that up. Next the 42 is revealed, then 84, then 2, then 16, then 15, then 19, 7, 8, 9. So all these you will automatically reject because you want to see how the numbers look like. So remember that you have not seen the remaining 25 minus 9, okay, which is 16. So you have not seen the remaining 16. You've only seen the first 9. You'll reject them all. Now you'll see, well, if I find a number that's larger than 84, I'll accept the first one that is so. So you look at 28, you'll reject that, 32 reject, 23 reject, and then you'll see 91 and you will go ahead and accept. And I'm going to change to the next slide where we've kind of explained this. So notice that you will reject the first n. So, that is reject, 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 reject and reject. So, that is the red color rejects of the first n over e, which is 9. Then you will reject this because it is smaller than 84, reject this is smaller than 84, reject this smaller than 84, and then you come to 91 and you will go ahead and accept it. At this point you would say stop. Now, turns out in this case we got lucky, all right. If you notice, 91 is the largest, okay, is the largest. So, we did really well. This rule really helped us. I promise you, this example was one in which this was the first randomly selected numbers that I threw in, and it turned out that I was lucky enough that this worked out for me. I am going to show you next when this could kind of mess up in some situations, which we will see in the next slide. However, I do want to pause for a moment to let you know that this problem, why this is optimal, is nicely derived in a Wikipedia site. Now, I want to pause for a moment to let you know that in general, Wikipedia is written by people, I'm sorry, not the whole Wikipedia, but articles in the Wikipedia are written by people who are considered, who are, who does not have to even be an expert, but who are someone who knows the topic somewhat well and has written something up. Very nice of them, but it's not always that a Wikipedia article is going to be absolutely accurate, okay. So, therefore, you want to be a little bit careful. However, from what I looked at for this article, if you search for secretary problem in Wikipedia, you will actually find this, and you will find a very nice proof. And the proof I don't want to go over for purposes of this course. However, I would recommend, if you have the opportunity, to go ahead and look at the proof and see why the stopping rule that we talked about, they're rejecting the first n over e of them, and then after that you keep looking, and the biggest number you see at that point, you go ahead and accept that, why that is the optimal solution, all right. Next, I want to just show you, so what if we had actually gotten the same 25 numbers, let's say we shuffled them and it came in some other order. Let's look at the first set, okay. So, let's say you first got 84, then 32, then 72 and so on. So, clearly the largest is underlined, and you would perhaps say, okay, at this point the first 9, my biggest number is 84, and therefore anything that is larger than 84, so reject, 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 and then reject, and I will see my 91 and I accept it. Again, we've been lucky, we actually picked the biggest number here. So, 91 is the largest. I'm picking the same example, I'm shuffling them up just to show you that there is no guarantee that this was the order in which we got the numbers, right, because there are 25 factorial ways that I could have actually selected these numbers. So, there is no guarantee that 91 actually is the one that we're going to pick, but somehow we got really lucky in the first 3. So, what I did was I wrote a little program and asked it to shuffle these numbers up. So, it turns out in the second example as well, we again have this 84 in this first set of 9, and therefore anytime I see a number larger than 84, which happens to be 91, we pick that and we've done well. Now, let's look at the third one. Again, this time it's not 84, but it's 82 that's the largest in the third set, and therefore anytime I get a number larger than 82, I say let's do it. And turns out the first 4 are not, and then I come to 91, and then I'd go ahead and say yes. So, we have been lucky in the first 3. Now, let's look at this example 4. Now, what happens is our friend 91 is in the first n over e, the first 9 itself has it. So, there is no chance for you to pick the best one. So, it turns out that none of the other numbers are actually going to beat 91, we know that, and therefore, you will pick the very last one. Well, I'm just saying that you were, according to a rule, you'll reject that as well and you'll be without a secretary, but on the other hand, what one would do is go till the very last one and select the last one, okay. Now, you could have, I'm sorry, this is a wrong sign. Now, you could have been more clever and say, okay, I have a different policy, every time I get a number that's even somewhat close to the largest, I'll pick that. You could do those types of things, and it's not clear, it's not easy to prove that that's optimal, but it's possible that it's a reasonable strategy. Now, let's look at another example. In this case, what happens is the first 9 of them has 82 as the largest, and we say every time we see a number that's larger than 82, we will say that's it. So, now what happens is our friend 84, that was the best in the first couple of examples, shows up before the 91. and we look at it and then we say, oh, we go ahead and pick the 84 and we miss out on the 91 that's coming much later. Now, this is a reasonably good solution anyway. However, that's one of the downsides, because you do miss it a few times. Now, let's look at the next example. Here again, the 91 has showed up. Every time 91 shows up in the first 9, you are never going to beat that 91, and therefore you will go to the last number and pick that. So that's not going to work out. Again, the next example also has a 91 in the beginning, and therefore you will not pick any number that's larger, and therefore you'll be settling down with the very last number that you see. Now, interesting enough, in the next 3 examples, and again I did not make this up, I actually randomly generated. If you look at the next 3, 2 of them, 91 ended up being the last one, and you ended up picking it, and 91 is here and you ended up picking it because fortunately my 84 came later. My 82 was stuck here, and therefore I got lucky. Otherwise I could have been picked 81 for, as a matter of fact. Any different things could have happened and we got lucky. So what I'm going to do is, this is the last slide, but I'm going to do a little demo. Let's try to do this in Octave. Okay, so what I'm going to do here is I've written up a program, and I will share this program with you. So be sure that you go to the website and download this program, and I would encourage you to play with these numbers a little bit. But I want to go over the program a little bit. So the first step is, so this is a program, or this is a code that is going to help us solve the secretary problem. So first step is, like always, like I said earlier, is to clear so that you don't have variables that were there from before. Once again, we load the statistics package. By once again, what I mean is from the previous lectures. Then in our slides we use n equals 25, but here I'm going to let the user pick a number. So this also is a little user GUI, if you will, not graphical, but at least user interface. So let's say I let you pick a number between 20 and 40. If it is larger than 40, it gets a little bit cumbersome. Of course it will work. You're welcome to put 10,000 if you want to when you try it, but let's say you put between 20 and 40. Now, by explore, remember you're first exploring. You're exploring the first n over e of them. So exp1 is e raised to the power 1, which is e, and n over e, and I take the floor of the function because I want an integer. So therefore I take the floor of that, and I would go ahead and explore. Okay, so I'm sorry, that's my value. So whatever number I take as n, I divide it by e, and that gives me how many I want to explore. In case of 25, explore will be equal to 9. All right. Then my program will say, okay, we will generate the first. We will reject the first explore of them, and then we will see what we need to do. So this is what we would do. I have a little index that says I go from 1 through all the way to n, because I keep revealing the numbers as they go. We will keep rejecting the first n over e of them, okay, and then we'll give you the choice. Do you want to keep or do you want to reject? Okay, so the key in this is I have really diabolically generated some numbers. Okay, let's look at this. I first generate a random number q. Now this q is 1 divided by an exponential. So remember that exponential distribution comes up with some really small numbers from time to time. So, and at times it could be larger than 1. So this the mean is 2. Sometimes you get a number smaller than 1. Sometimes you get a number way larger than 1, and we don't know what it would be like. So that will be my q. Then I have an r, which would be the inverse of a gamma distribution, where I randomly pick an inverse of the CDF and I get another number. So I have 2 random numbers which I use as my parameters of a normal distribution. Okay, this is going to be the mean parameter, this is going to be a standard deviation parameter, and I get the random number and I put it into Octave, and I create a normally distributed random number. Take its absolute value, because remember normal can be positive or negative. So I take the absolute value. So that's my number that gets generated each and every time. Okay, so if you think about it, and when we see the examples, you'll see these numbers could go all over the place. Okay, and I've really picked some nasty ones. If I pick some nice distributions, actually you'll see we do pretty well. This would be pretty nasty, and I don't know how many times we're going to do well. So what we do is we will explore for the first n over e. Then once that is done, hence else, what we will do is we will say, okay, my decision is 0, that means I will reject. So if I've been rejecting, till I reject, I'll keep releasing numbers, and I ask you the question, do you want to keep this or do you want to reject? And once you have accepted, then what it will do is it will reveal the remaining numbers. Okay, it will just reveal the remaining numbers to see if you actually pick the largest one or not. Okay, so let's play this. It's an interesting game that we play, and then you keep doing this till you get all the n. So the name of this program is called SEC secretary underscore demo. So we do SEC underscore demo. I understand that the font size here is pretty small and you have to really squint your eyes to read. If this is difficult, I'm going to talk through this. You're welcome to download the program and exactly type what I'm typing and see on your screen how this is working out. So I'm going to hit SEC demo and hit SEC underscore demo and hit enter. So as we expect, the first question that it asks me is pick a number n between 20 and 40. So let's say I pick 30. Okay, so I'm picking n equals 30 and I hit enter. Then what it does is it gives me, so it tells me that the first 11, so I'm going to reject the first 11. So it will generate 30 random numbers, but one by one it will reject the first 11, that's n over e, the lower bound of n over e, and it will reveal some value. So the first number it reveals is 109.64, okay, or 65. The next number is 14, the next number is 0, the next number is 0, 0.42, 0.6, 0.35, 3.99, 6.9, 1.5, 0.85, 1.07, and this last number is 0.56. So these are the first few that it rejected. If you notice, the decision is to reject. So clearly the largest one is the very first one we've seen. So anytime I get a number that is greater than 109.65, I'll say let's use that. Clearly the first number that we have is not larger, so we are going to reject. So I'm going to put 0. Okay, so I'm going to reject. The next number is 0.67. Again, we will reject. Okay, so I'll do 0. Now, when you run your program, because your random numbers could be different than mine, you might get a different set of numbers. So don't be surprised when you don't see the same set of numbers. Okay, that's because it's randomly generating. Now, the next number is 0.95. Clearly, we will reject that because we need a number almost as large as 110. We'll reject 1.40 as well. This is finally we get a large number, 57, but still not as close as 109, so we will reject. 5.8 we will reject. 0.50 we will reject. 7.82 slightly larger, but still we'll reject. 0.2 too small, we'll reject. 0.5 too small, we'll reject. 0.56 too small, we'll reject. 25, now we're getting better, but still not quite as 110. Reject, 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 reject. So now 54, well, by now, in real life you'd say, well, we'll just take this 54 because we don't seem to be getting good numbers. In real life you will accept this, but I'm going to go ahead and reject it, okay, because that's what our rule says. I will reject it and I will reject. So basically this one you would end up accepting, but I'm going to press 0 just because I think it doesn't say what to do at the very end. So let's try this one more time. Let's do secretary demo a second time. Now let's pick a number between 20 and 40. Let's just pick, say, 34. Okay. Now what happens is it picks the first 12 and rejects them all. If you look at it, what is the largest number that we have here? It is 6.35. Okay, 6.34. Okay, 6.34 is the largest number. So you look at 0.04 and you will reject. Okay, and then the next number is 26. So it's bigger than your 6. So this 26 is larger than the biggest number we've seen so far, which is 6. So I will accept this. But after I accept, what will happen is it will tell me what is my 15th number through my 34th number and see if my 26 was the best. So it turns out my 15th number is 1 point. So you look at all these numbers, then 0.8.242. So we ended up being lucky this time, and we actually did select the best number. Okay, I should stop on this wonderful note, but let me just be a little bit masochistic and see what happens again. Okay, let's try a third time. Let's say we pick 37 as my number. So we will reject the first 13. And then so if you look at it, all the numbers are somewhat small except this 3.99, so almost a 4. that's the largest number I see. So, you look at 1.56, you will reject. Okay, so, if you get a number larger than 4, you will accept. Right away you got one, and I will accept this, and then I hit enter. Turns out that if I was a little bit more patient, I would have hit this 50. That would have been my best choice, but I settled in for a number that was larger. So, again, so it's not always that you will get the right answer or you will get the best one, but you tried. Okay, so the policy says I will reject the first few and I take the next number that's going to be the largest that I've seen thus far. Turns out in this previous case, about almost 4 was the largest number. So, anytime any number I see bigger than 4, I'm going to accept. And when I saw that, I accepted it, and turns out soon after that I got a ton of numbers that were larger than 4, 7, 7, 50, 9 point, and so on, 4.7. We have a bunch of numbers, but 5 point here, one more. So, we have about 5 numbers that are larger, one of them being really large. So, we missed getting those. So it turns out that, like I said, this is not guaranteed to give you the largest number, but this is a policy that will help you get the largest number with a high probability. Okay, thank you.